So one of the things that comes up on some of the reviews that I'm going to give you, and I think I have some questions that are similar to this on your test next week, is how do you match the graph? If you have the graph of something, how do you match it with the derivative graph? So one of the things that is key for matching a graph and its derivative graph is to understand what the derivative is, right? The derivative graph is a bunch of points that represent the slopes of tangents to your first graph. That's what your derivative graph is, because your derivative is your gradient function. It's a slope function. It finds the slope of any tangent line to any point on your graph. So if I were to pick a graph, I've got a bunch of graphs here. If I were to pick one of these graphs and want to draw the derivative graph based on just looking at that graph, how would I do that? So the first one is just a straight line, okay? And that straight line has a negative slope. So if I pick any point on here, well, the tangent at that point is exactly the same as the slope of that line. So we have to decide what would be a reasonable graph for this. It's going to be, what's the slope of that line look like? Maybe -1. And so at this point, I would have -1 as a slope. And no matter where I picked a value on there, I'd always have -1. Another thing you could do in this situation is say, oh, that's a line. I know the equation of that line. That line's equation is -x plus 2, because it has a y-intercept of 2 and a slope of -1. So if I did the derivative of that, it would just be -1, which is that horizontal line. So that example, though, is an easy one that we can actually figure out the equation for. But we have some later on, like number 5. When you look at that, you can't just say, oh, I know the equation of that graph. I recognize it right away. No, that's not the case. So what we're going to do for one in equation 5 is sort of set up some steps that we can use to help us match the graphs. So number 1, the first thing we're going to look for is, can we find all maximum and minimum points on the original graph? So I'm looking at number 5 here. Maybe I'll zoom in to number 5, make it even bigger. Yes, that's good. You can say this is a cubic, so the derivative is going to be a parabola, but this one might be to the power of 5. You don't know for sure that it's cubic. It might be the power of 5, but if we start with all maximum and minimum points on our original graph, so on this one I have a local maximum there and a local minimum there. We're going to learn that we're going to use local because it is a minimum in its area, but it's not necessarily the absolute minimum of this function, because this function does continue down forever. But if you drew a tangent at a maximum or a minimum, what would that tangent look like? It would be a horizontal line. Does that make sense that anywhere where you have a maximum or a minimum, you're going to have a horizontal line as a tangent? And what's the slope of a horizontal line? 0. So finding finding all maximum and minimum points on the original graph, these will be zeros or x-intercepts on the derivative graph. You can write this down in at the back page of your notes if you like. So what does that mean? I have a maximum at -2. That means on my derivative graph, it would be 0 there. I have a minimum at +2. That means on my derivative graph, it will be 0. So the first thing we're going to find is all those maximum and minimum points, and then those will be the x-intercepts of our derivative graph. The next thing you're going to look at is in between and on either sides of those x-intercepts. Let's start with in between. If I go in between that maximum and that minimum, and I pick any tangent in between there, let's say I pick one right here. Do it in blue. If I drew the tangent to that point, would it have a positive slope or a negative slope? Negative slope. Can you see that any point that you would choose between those, no matter where you draw your tangent in between those two green x-intercepts, you will always have a negative slope. And so, based on that, you know that your graph is got to be, your derivative graph has all negative slopes. It needs to be below the x-axis to show negative slopes. Now, I just estimated where it was below. I don't know how far below it needs to go at this point. I just estimated. If I drew this line, maybe I thought, oh, I think that line has a slope of -4. Well, then that would match up perfectly with that point at -4. But I don't know exactly. I'm using a little bit of an estimation. But again, what we're trying to do here is we're not trying to graph it perfectly. What we're trying to do is how do we match graphs so we get an idea of what the graph looks like so that later we can match it with another one. So what we're doing right now as a step 2 we're checking the slopes of tangents in between and on either side. And we're just checking if they are positive or negative. So going back to the one that we just did, we found out that in between, the tangents were always negative. Can you see to the left of the maximum that if I drew any tangent on this stretch, no matter where I drew it, see if this pen is set up. Can I make something sparkly? No, yeah, it's ready. Okay. It's how I wanted it to be. So if I drew a tangent here, or a tangent there, or a tangent there, no matter where I draw a tangent to the left of that point, it's going to be positive. So we can show that on our graph that this part has to go up. Oh, I thought I had it set up, but apparently it's not set up. Go like disappear. And same thing here, any tangents to the right of that minimum will be positive. So it has to go up. And they're going to get steeper and steeper and steeper, so our graph is going to go up as well. Step 3, which we'll sort of use in context with the question, if you can recognize the type of function, then you know the shape of the derivative. That doesn't spell derivative. So what does that mean? Well, someone said, that's an x cubed graph. If I recognize the original one as an x cubed graph, the derivative of an x cubed graph is an x squared graph. So then I would recognize that it should be something like a parabola afterwards. Yes?
Can you for sure say it's an x cubed? Why do you put arrows at the end? What if it goes back up?
Right. In this case, we don't know that it doesn't come back up here and go up after this, right? Then it could be an x to the 4 graph, right? But based on what is shown there, a best guess for this would be an x cubed graph. And if you were given a graph that had other characteristics, sort of the rule of thumb is if I'm ending it here and it's going to keep on going, I'm letting you know that it keeps on going down forever. It's not like, right? Because I could give you a graph of this one and just call it a straight line. And you'd think it's a straight line, but I'm just giving you a tiny, tiny window where it looks straight. Right? And it's not actually straight. That would not be a fair way to assess. Right? Guess what the graph is, and please guess all possibilities based on whatever I want to do after that you can't see on the graph isn't really fair. Yeah. So what we're going to do is this idea. The key thing is look for your maximum and your minimum because those become x-intercepts. Because the tangent at those values is horizontal, meaning that they have a slope of 0. That's the big idea. Then in between, any tangent I have is negative. That means your graph has to be negative in between there. And wherever your tangents are positive, your graph will be positive. All right.